Welcome, everybody. Good afternoon, good evening, or good morning, depending on where you are. It's my pleasure today to present this seminar by Dr. Marika, Holland. It's the second seminar of a series of webinars on the Arctic system and its predictability that we organized here at CMCC. So it's really a pleasure to have today, after the first seminar we had last week from Amy Solomon, to have today Dr. Marika Holland from the Climate and Global Dynamics Laboratory of the National Center for Atmospheric Research, NCAR. She's gonna speak today about predicting Arctic sea ice from seasonal to multi-decadal timescales. So first of all, I'm gonna introduce Marika, even if I don't think she really needs it, but you know, just in case. Marika is a senior scientist in the Climate and Global Dynamics Laboratory at NCAR. And of course, her research is focused on the role of the sea ice in the climate systems, including also long-term sea ice change, sea ice predictability, and in general, polar climate variability. She has extensive experience in using climate models, but not only using climate models, because she had been very active also in the development of improved sea ice models for the climate simulations. Marika has served as a co-chair for the Polar Climate Working Group of the Community Earth System Model and chief scientist for the Community Earth System Model project. Very importantly, she has been a contributing author for the IPCC third, fourth, and fifth assessment reports. And, you know, as I guess is a fully deserved recognition of all her activities in the field, in 2019, she was awarded the International Arctic Science Committee Medal. Okay, so this is, you know, this brief, in short, in a few words, the long, amazing career of Marika Holland. Before giving the floor to Marika, it's my duty to introduce a little bit CMCC for those who join our seminars for the first time, just to let them know who we are. For those who are regular fellows, followers of our seminars, sorry, it will be a little bit boring, but please be patient. So the Euro-Mediterranean Center on Climate Change is a non-profit research organization that was established in 2005, so recently a new reality in Italy. In 2015, the center became a foundation, and as you can imagine, CMCC is a scientific research center on climate change, but also on impacts of climate change with on different sectors. So interaction with the environment, the society, the world of the economy and business as well. Our main challenge and our main objective is to stimulate sustainable growth, protect the environment, and develop strategies for the adaptation and mitigation of climate change. CMCC is organized in a form of a network of different divisions distributed basically all over the Italian country, as you can see, from Milan to Bologna to Venice, Viterbo, Caserta, Lecce, where we had our headquarters and also the supercomputing facilities, and even in Sardinia, Sassari. CMCC scientific activities are distributed among 11 research divisions. I'm not gonna read, of course, all the divisions. If you're interested, all the information, you can find all the specific detailed information on each of the divisions on the web page. But of course, all the divisions share different knowledge and skills, all in the field of climate science. So CMCC basically collaborates with a lot of scientists, but not only, also economists, technicians, which work together in order to provide full analysis of climate change and climate change impacts on different sectors, from the energy sector, to the agriculture, to the marine and land ecosystems, to coast, water resources, health, and economics. And CMCC, as I probably already said, also supports policymakers in setting and assessing cost and mitigation and adaptation policies. Last, how do we present ourselves in the international and international community through outreach activities and tools, the traditional tools of scientific publication, events like the one you're following right now. So a lot of webinars organized by CMCC, communication through traditional tools, and more advanced, sophisticated tools. But the thing that I would like to focus more is about education. So CMCC is deeply and more involved in several graduate programs in many universities in Italy. And so the number of PhD students that actually are followed by CMCC researchers is growing a lot. And this is really, I think, the most important thing to keep the interaction with the young scientists. Okay, so that's it about the presentation of CMCC. Let's come to the, some technological details on how this webinar will go on. For all the participants, during Marika's presentation, your audio and video will be deactivated by default. So if you need to intervene, also during the seminar, you can start to intervene through the Q&A section, question and answer section. So you can write directly questions in this section. And at the end of Marika's seminar, you can use also during the Marika session, you can start to raise your hand if you want directly to ask questions at the end of the seminar to Marika. So the moderator will give you the floor. What else? The webinar will be recorded and it will be also uploaded on CMCC YouTube channel. Here is the address. If you have any further question about the webinar, you can directly email to us, or even more efficiently, as I guess it would be a scientific question to Marika, you can send the question directly to Marika. Just the last slide is a reminder of the next two seminars that are part of this webinar series on the Arctic system and its predictability. We will have next Monday on the 20th of September, Mitch Bushuk from Princeton, from the GFDL laboratory in Princeton, and the week after, on the 28th of September, Ed Blanchard from the University of Washington. So please keep following us, even with these other seminars. Okay, I stop and I leave the floor to Marika. Marika, the floor is yours, and thanks again for accepting the invitation to give this seminar, CMCC. Thank you very much.
Yeah, so thanks so much for inviting me to to talk. And I think as soon as Simona stops sharing her screen, I will share mine. Okay, so hopefully you can see that, and the slides are clear. So thanks again for the opportunity to talk with you today. So I'm going to be sharing with you some work we've been doing on predicting Arctic sea ice across timescales. And I'm going to talk a little bit about the interaction of these timescales. So how long-term sea ice changes can also influence seasonal predictability characteristics of the sea ice. So just a very brief outline. I'm going to start with a background, and I'll discuss some of the sea ice processes and the fact that those are climate state dependent. I'll then move on to the implications of that for predicting sea ice on multi-decadal timescales, and then the implications for predicting sea ice on seasonal timescales in this rapidly changing Arctic climate. And then I'll end with just some final thoughts. Okay, so on to the background. So I think this maybe goes without saying, but I think it's useful to put all of this into context of what is happening within the Arctic system, and why there's this very strong interest currently in being able to predict sea ice across these different timescales. And of course, a lot of this is because the Arctic is changing very rapidly and very dramatically. So this shows sea ice concentration trends from 1979 to 2017. The gray area in the middle here at the pole is just where the satellites don't sense, so there's no data there. But you can see, there's large scale loss of sea ice, particularly in the summer. This is September here, across the Arctic. And so that's led to a lot of interest in marine access and safe marine access within this region, which again speaks to the need for reliable predictions. I think it's important to note that this sea ice loss is part of a larger systemic change across the Arctic. And these things are all interacting. So we're seeing increases in the melting of the Greenland ice sheet. We're seeing rapid warming across the Arctic. This shows changes in air temperature in 2020 relative to the 1981 to 2010 period. And the Arctic is warming at over twice the rate of the globe as a whole. These changes are also impacting the land, and we're seeing increases in wildfires. That's leading to increased biomass burning emissions that are then feeding back onto the system back through black carbon deposition, but also changing cloud characteristics in the Arctic system. And all of these things are conspiring to impact coastal erosion, loss of sea ice leading to more wave action on the coast, warming of surface ocean waters, thawing of these ice-rich permafrost bluffs. And so, of course, these are having dramatic impacts on people living in the region. So this Arctic sea ice loss is part of this large-scale changes happening across the Arctic system. And of course, as part of this, we'd like to know where things are headed. So this shows the Arctic September time series of ice extent that's been observed from satellites from 1979 to 2020 here. The blue line here is just a linear fit to this. And so you can see that, from one year to the next, there's a lot of variability in the Arctic sea ice system. And that's on top of this overall long-term, very rapid sea ice loss that's occurring. So of course, we'd like to know what's going to happen to the Arctic system next season, next year. And so this, of course, raises this issue of predicting sea ice and how predictable is the sea ice cover on these different timescales. So that's going to be the topic of my talk. Before I get there, though, I'm going to talk about how processes in the sea ice are climate state dependent, because this has very important implications for our ability to predict Arctic sea ice, and also how that predictability of sea ice could change in the warming climate. So one of the aspects of sea ice that is climate state dependent is the growth of sea ice. So here you can see on the left a schematic of the sea ice floating on the Arctic Ocean. You see ice of different thicknesses covered by snow. There can be open water areas, cracks in the sea ice in the form of these leads. And it's important to note that thinner ice actually grows more rapidly, subject to the same atmospheric forcing. And that's because ice growth occurs because of the conduction of heat through the sea ice. Because sea ice is a strong insulator, thicker sea ice will have reduced conduction and reduced ice growth. So thinner ice grows more rapidly. So as we transition this system to a system with more thin ice regions, we actually expect to have increased growth, and several studies have shown this. It's also important to note that this relationship is nonlinear with ice thickness. So this shows ice growth here as a function of ice thickness. You can see that it's nonlinear. It actually goes as 1 over the thickness. And this causes a negative feedback on ice thickness, so a stabilizing feedback, which is stronger for thin ice. So that's important. As I move through my talk, I'll refer back to this. That's not the only aspect of sea ice, however, that's climate state dependent. Summer open water formation is also dependent on the sea ice thickness. So again, if you go back to this schematic here of sea ice on the Arctic Ocean, as you're melting over the summer, you would expect that these thin areas would melt out first. So as we increase thin ice within the Arctic Ocean, we actually increase the amount of open water that can form. This relationship is also nonlinear with ice thickness. So this shows the amount of open water formed per centimeter of ice melt as a function of ice thickness. And you can see that this relationship is also nonlinear. So as we move into these kind of thin ice regimes in the Arctic, you can get a lot of open water formed for the same amount of ice melt, the overall ice melt. Of course, this has implications for the surface albedo feedback. As you expose that dark open ocean, you increase the amount of heat absorbed in the ocean, leading to further warming in the Arctic system. Okay, so those are some of the sea ice processes that I'll be sort of referring back to in the talk. So how do these things conspire to affect the multi-decadal prediction of sea ice? Well, on these timescales, the predictability that we're talking about is really a boundary value problem. So predictability, of course, can arise from these different aspects of the system. Predictability of the first kind, which is an initial value problem. It depends on knowing the initial state of the system and being able to predict the evolution into the future. Of course, that predictability of the first time has a sensitive dependence on the initial conditions and the fact that we have errors in our initial state, and those errors will grow over time because we're dealing with a chaotic system. And so I'll talk about this kind of predictability in the second part of my talk. But in this first part, talking about multi-decadal sea ice predictability, this is really a boundary value problem. So on the schematics, it's indicated by the red shading. So basically, we're trying to predict the statistical properties of the climate subject to some external forcing. And of course, the external forcing that is impacting the Arctic primarily is the rise in greenhouse gases. So, we're asking the question, how does the Arctic sea ice mean state, and also variability, the spread that we can expect just due to internal variability, how do those things respond to rising greenhouse gases? So in order to use, to address this question and also initial value predictability questions, I'm going to be using coupled climate model simulations. And I'm going to be looking at the change in properties over time. Okay, so I'm particularly going to use this CESM large ensemble. That large ensemble has 40 ensemble members run with the exact same model. identical external forcings, meaning changes in greenhouse gases, volcanic emissions, solar variability at the top of the atmosphere. The only difference across these ensemble members is a small round-off level change in the air temperature when they're initialized in 1920. But because the system is chaotic, those errors will grow. And so over time, these simulations will spread, and we see that they're fully spread within a decade or so. So we can assess a forced response in these by looking at the average across all of those simulations, since all of those simulations are subject to the same external forcing. And we average out the noise of internal variability. We can then quantify internal variability by looking at the variations around that ensemble mean. So basically subtracting out that ensemble mean, what kind of internal natural variability does the climate model simulate? So that's how we're going to quantify these things. Okay, so what does this simulate for projections in the 21st century? So this shows September Northern Hemisphere ice extent. The black line here is the ensemble mean. So again, that can be considered the forced response of the system, the response associated with this boundary forcing of rising greenhouse gases. And then the range across the members is shown in blue. The observations is shown in red here, and you can see that it lies within the envelope of our simulations, but at the lower end. So overall, you see that there is a strong indication of a boundary forced predictability on these multi-decadal timescales. We see this loss of sea ice. You see that across all of the simulations, although it's happening at different rates. Again, we can also quantify the internal variability in those projections. So that just is the variability that arises due to the internal climate dynamics of the system. So this is shown here. This is 40 individual lines on this plot. Each of those is an ensemble member, where all I've done is subtracted out the ensemble mean. So it's the anomaly from the ensemble mean in the September ice extent. And what you see is that from 1920 out to 2100 here, in the 20th century, there's a lot of variability. The ice can vary, plus or minus 1 million square kilometers, and that's out of a mean of about 8. So that's a considerable amount of variability, but it's also quite stable over the 20th century. The ice variability then actually grows in the early part of the 21st century. That's because the ice is thinning, and that ability to melt out large regions of the ice pack is very dependent on the summer weather. So you can have a lot of variability in that, leading to a lot of variability in the end of summer sea ice extent. We can quantify this further by just looking at the standard deviation across these simulations and how that varies with time. So again, you see it's quite stable over the 20th century, but then it peaks in the early part of the 21st century, meaning that the system is just more variable with a thinner ice cover. That's true in September, which is what the black line shows, but we also see that it occurs in other months, August, July, starting to occur in June at the end of the 21st century in these climate simulations, as those months start to reach thin ice conditions and as the September sea ice melts out. Okay, so that's what we expect for these changes into the future. How do these different factors, the declining ice area, the thinning of the ice pack, this change in the summer ice area internal variability, how do those things conspire to affect the transient summer sea ice response to rising greenhouse gases and our ability to predict that? So in order to answer this, I'm just going to flip through some of the individual ensemble members, because I think it's very illustrative to see what these different ensemble members show and the amount of internal variability that can occur. So the differences between what I'm going to show you in the next several slides in the black line is just due to the internal variability simulated by the climate. So this is, again, just the natural variability that arises from internal climate dynamics. So in this simulation, you can see that the model has a trend over the historical record that's quite similar to observations, and it reaches, near ice-free conditions around the middle part of the 21st century. We also see that just because of internal variability, you can have sea ice simulations that have much less sea ice loss over the historical record, still reaching ice-free conditions around the middle part of the 21st century. Other simulations that have very anemic sea ice loss up until 2020 or so, and then rapid ice declines. Others which look very similar to what's been observed, but then might have a decade or so of increasing sea ice conditions and stable sea ice cover before they have a very rapid sea ice loss event. And of course, this is just due to the combination of this boundary force signal, strong increases in greenhouse gases that are pushing the system to reduce sea ice, on top of this growing internal variability that it can affect things even on these decadal and multi-decadal timescales. So if we put all this together, this again is just showing those 40 ensemble members, a sea of black lines here. What we see is that there is this strong boundary forced signal. It's detectable. All of them, when you look over multi-decadal timescales, have sea ice loss. But there's also this large and growing internal variability, and that leads to possibility of decadal increases in sea ice, even in the 21st century, and also instances of rapid decadal decline. So all of those things impact our ability to predict the Arctic sea ice cover. But that boundary forcing is very strong. And so we do see that a forced climate signal emerges from the noise actually quite early in the system. So this shows from a number of different climate models now, which all have large ensembles, so we can do this kind of analysis, the time at which a forced signal emerges in the September sea ice area. And so basically these lines become dark, solid when a force signal emerges for the following decade. So this is looking at sort of decadal sea ice changes. And what we see is that in all of these different climate models, a forced signal in the September ice extent emerges at the kind of turn of the 20th to 21st century. So quite similar years here, meaning that the conditions in the 21st century are statistically different than what we saw in the early part of the 20th century. But there are other aspects of predicting Arctic sea ice on these multi-decadal timescales that are very challenging. So for example, predicting the timing of a September ice-free Arctic is very difficult because of this internal variability. And that internal variability causes an irreducible uncertainty of about 20 years for the timing at which we first reach ice-free summers. And that's quantified here on the right panel, where you can see a histogram in blue of the year at which the Arctic first reaches ice-free conditions in September. And you can see that that differs by about 20 years, purely due to internal climate variability in the system. The green bars here are just for a different forcing scenario with lower greenhouse gas emissions. But again, you see that across the green bars, something like a 20-year difference. So it's very challenging to predict the year at which we would expect ice-free summers to first occur in the Arctic. And this is work that was led by Alexandra Jan. Okay, so that gives some information on sort of these long-term multi-decadal sea ice predictability and some of the challenges in predicting sea ice on those timescales. But because those climate processes, those sea ice processes are climate state dependent, that long-term large-scale sea ice loss and thinning in the Arctic can also impact seasonal predictability characteristics of the Arctic. Okay, so this now is looking at this predictability of the first kind, initial value problem predictability. And so we're basically going to ask the question of, do seasonal predictability characteristics change in the warming climate? And there's some evidence from just idealized systems that, this is a reasonable question to ask. So this is just sort of illustrated here using the Lorentz butterfly. And so you can envision, if you had a cloud of initial states that you're initializing a prediction with, and then you're marching that forward in time, how closely tied, how reduced or how small the error growth is in those initial conditions affects your predictability and the timescale of that predictability. So you can see on the left here, this cloud of initial points, they actually stay very tightly grouped over time. So that would suggest that those forecasts have predictability for a quite long period of time. But if you start in a different area of phase space with, similar cloud of initial states, you can see that those errors grow much more rapidly, and on the right panel here, very rapidly. So that suggests that we could have different predictability characteristics depending on where we are in phase space. And for the Arctic, that suggests that predictability characteristics could be different in a cold, thick, ice-covered Arctic relative to a warm, thin, ice-covered Arctic. So we wanted to address this question. And in doing so, we used sort of idealized experiments from the community Earth system model. So basically, we set up perfect model predictions. So basically, we're using the model to predict itself, just to try and understand what the inherent predictability characteristics are within the context of the climate model. So for each decade from 1980 to 2030, we initialized ensemble predictions, and we took the initial conditions for those from our CESM1 large ensemble, so this free running climate model, where we have 40 simulations. So we took 4 different states for each of these decadal periods, and then we ran 1-year predictions, where we had 15 ensemble members in each of those. And so again, we used 4 initial conditions representative of the decadal climate. Now we know, because we're using output from the climate model, we know that initial state perfectly. But we add a small level of round-off level air temperature change across our ensemble members. And of course, that error will grow over time because of the chaotic system. So this shows an example of the experimental design here on the left. So this is just for the Arctic Ocean ice volume in these simulations. The range across the free running large ensemble is shown in the dashed lines. And then we have these 4 different predictions, and we initialize them, with conditions that sort of span what we get just due to internal variability, in this case for this 1980 set. And then we run predictions into the future. Those have 15 ensemble members. So there's 15 green lines, blue lines, red lines, black lines. And you can see that they're very tightly constrained initially, but at several months into the simulation, they start to diverge, and you see them diverge much more strongly as you reach the summer melt season here. So we can use the CESM large ensemble, which is just a measure of internal variability, not this initialized predictability, to assess the predictability in these simulations. And so basically, we can compare the initialized ensemble prediction spread to internal variability from the climate model. And when that prediction ensemble spread is considerably less than internal variability, it means that there is a predictability in the system. So this shows that again for this Arctic Ocean ice volume, for this 1980 ensemble set. The blue here is basically the prediction ensemble variance in that Arctic Ocean ice volume. And this is internal variability. And you see that it's always considerably less throughout the year of our simulation, indicating that there is high predictability for ice volume on these sort of annual timescales. So what about ice area, which is a metric that's more important for marine access considerations? So I'm showing just the same thing here. This is, but for ice area variance within the Arctic basin. So these are all initialized on January, but I'm showing from June through December here when the Arctic Ocean starts to have ice-free regions. And you can see in this case, for this 1980 ensemble set, that the variance in ice area in our prediction ensemble is basically the same as that due to internal variability. So this indicates that there really is no predictability for ice area for these January initialized predictions in this 1980 ensemble set. And you might as well just, pick something from the historical record or internal variability as your prediction. What about these other decades? So this shows same thing for 1990, 2000, 2010, 2020, and 2030 here. And what you see now as you move into this thinner sea ice regimes and a warmer climate is that these things do start to diverge. And so our predictions become actually indicate that there is predictability in the system in these warmer, thinner decades. The prediction ensemble variance is considerably smaller than that due to internal variability. So there is this suggestion that the predictability characteristics change in a warming climate. This is true if we look at these, kind of hemispheric metrics of ice area. It's also true if we look at the ice concentration across the Arctic basin. So in this case, blue colors here would be more predictable. And you again can see that, the predictability characteristics change 1980, 1990, 2000, 2010, and in particular, 2010 is the most highly predictable, and we can quantify that using these prediction skill metrics. That's true if you look across the basin. It's also true if you only consider the regions where ice is actually highly variable, which are the areas between these black lines. So I've kind of shaded out the interior of the ice, which might have high predictability, but it also has very extensive sea ice cover. And so it's not really of consideration for things like marine access. So what causes this loss of ice or this change in ice area predictability? So we can use information from previous work that's indicated that ice thickness is an important predictor of summer ice area because those thickness anomalies are long-lived, and those thickness anomalies affect how much meltout you have in the summer. So we can use that information from previous work to think about the loss of predictability and the fact that the loss of predictability can be related to the growth of ice thickness errors in the system, and then how those ice thickness errors affect how much meltout you have in the summer. And we can quantify that just by looking across our ensemble simulations, just shown here for one prediction ensemble set, at how those errors in ice thickness grow, and we can look at the spread across these simulations to quantify that. We can look then at how that spread in ice thickness errors at the beginning of the melt season ultimately affect the September ice area by just looking at the regression line between those two things. So the regression of September ice area on the July ice volume or ice thickness. Ice volume is just the integrated ice thickness across the basin. And you can see that there is a strong relationship there. Okay, so we're going to quantify these things for our different decadal seasonal predictions. And so this shows the growth of ice thickness errors starting here in January, where the simulations are initialized, and then moving until September. And what you see is that that ice thickness error growth is smaller in the warmer climate, this 2030, 2021 climate state. And that is because anomalies in thin ice are more strongly damped. And that's related to this relationship between ice growth and ice thickness that I introduced you to early in the talk. So what about how sensitive meltout is to those thickness errors? So here we're quantifying that again, just by looking at the regression of September ice area on the early melt season ice thickness. And you can see that this meltout sensitivity grows over time. So it's larger in the warmer climate. So both of these things are important for the loss of predictability in our simulations. So this growth of ice thickness anomalies from the initialized state, or this ice thickness error growth, is smaller in the warmer climate. But how those ice thickness errors affect meltout and ultimately lead to a loss of predictability in the end of summer ice conditions is larger in the warmer climate. And so what we find is that actually we have this sort of sweet spot for predictability in our 2010 predictions, because there's modest ice thickness error growth, but there's also a modest influence of those ice thickness errors on the summer meltout. Okay, so some final thoughts. I think it's very important to realize and note that sea ice processes and the related feedbacks associated with those are climate state dependent. And this leads to things like changes in internal climate variability of the sea ice system, changes in seasonal predictability of the sea ice system. So in terms of multi-decadal sea ice loss, the fact that sea ice processes are climate state dependent causes this growth in the internal variability of the sea ice area. And that affects our predictability of things like the timing of an ice-free Arctic state in the Arctic. It also affects seasonal predictability characteristics in a changing climate, leading to kind of this sweet spot of predictability that in our climate simulations occurs around 2010, but of course it'll be different in the real system. But these climate state dependent processes of sea ice modify the seasonal predictability characteristics of sea ice as we move through this warming climate that we're experiencing. It also has implications for differences across models, and I'd refer you to this nice paper by Masina et al. In 2018 that discussed this. So all of this implies that simulating a good present day sea ice state is really important for reliable predictions of sea ice, both on seasonal timescales and on multi-decadal timescales. So I'm going to stop and take questions. I did put my contact information here in case people have questions that we don't get to in the next several minutes. Please feel free to email me. I'm happy to continue the discussion by email as well. And so I'm happy to take questions. And I do want to just show a reference slide here because I referred to a lot of people's talk throughout this. And so, you know, in the video, I wanted to make sure that those different studies were acknowledged. So anyway, I'll go back to the question slide and yeah, and take any questions people might have. And thanks a lot for your attention.
Thank you very much, Marika. Thank you very much for this interesting talk and the skill that you had to synthesize so much work in half an hour. I think that's an amazing skill. So we already received some questions in the questions section. So I'm gonna start with this one. The first one that we received is from Franco Boscolo. It's related to what's going to happen north of Alaska. The question by Franco is whether a large area of low concentration ice north of Alaska will melt away. He refers this as a remaining question. If Franco wants to ask the questions directly or add more details, of course, he can do it.
Well,
Yeah, please go on.
I'll just start by saying I'm not quite sure on what timescale you're talking about. I do think that, you know, if greenhouse gases continue to increase and at the rates they are into the future, we will melt out most of the ice in the Arctic. I mean, it might take decades to do so, but you know, I think we'll start to see large scale losses in the winter sea ice as well if we continue to warm the climate in the way that we're doing. So again, I'm not quite sure what time scale you're talking about.
Well, this question arrived at the very, you know, quite early during your seminar. So I guess it was more referring to long time scales, decadal time. Yeah.
So I think on those time scales, we are talking about melting out most of the ice, especially in the summer, but it'll creep into the fall and winter more and more over time.
Okay, thank you. Coming to the second question by Deep Sankar, one of our colleagues here in Bologna, is interested about the Antarctic. So his question is, are there any similar projections indicating the loss of sea ice for the Antarctic as well, especially during the Southern Hemisphere summer?
So our climate models do simulate loss of sea ice in the Antarctic as well, as we warm the climate into the future. I would say that the sea ice simulations over the historical record in the Antarctic have been less skillful than what we have for the Arctic. You know, the Antarctic is a very different system, and there are different processes that play an important role. In particular, the Southern Ocean and ocean heat content and things like that are actually really important. So our climate models struggle a little bit, I would say, in the Antarctic. So we don't typically simulate increasing sea ice trends in the Antarctic that were observed until recently. And, you know, there's a lot of work being done to try and understand why that's true. So we do simulate ice loss into the future in the Antarctic as well. I think that is probably the sign of that is probably reasonable. The rates of that across the climate models, I think, are a little bit uncertain, given the fact that we do struggle to, I think, simulate some of the properties of the Antarctic sea ice cover.
Okay, so let's proceed because we are receiving a lot of questions. So I would like everybody to have the chance to have an answer from you. And here it comes François Massonnet. And so at this point, I think I will leave the floor to François directly to ask his questions, because it's a long questions and I'm sure he can phrase it better than I would do. François?
Hello?
Yes.
Okay. Thank you. Yeah, so thank you, Marika. It was a great talk. And my question was about your inherent predictability study. So the question is, do you think that the predictability estimates from these type of simulations, so perfect model estimations of the predictability, could they be underestimated compared to the real world predictability? And the question comes in the context of these recent studies, in particular from the Met Office, that looked at the North Atlantic Oscillation predictability, and they found that there was what they call the signal to noise issue, meaning that the fraction of predictable variability is actually underestimated in those models. So it's just a really open question to have your opinion, whether you think the same issue, signal to noise, could apply to the sea ice as well. Thank you.
No, that's a great question. I honestly don't think we know the answer, but I think it's something that needs to be looked into more carefully. I mean, it does seem like some of the work that Mitch Bushek and Ed Blanchard-Ricklesworth have done suggest that the climate models might actually be too predictable for sea ice on seasonal timescales. So kind of the opposite of the NAO signal to noise paradox. That's been done looking at sort of things like autocorrelation, persistence metrics from models versus observations. But again, our observational record is short. I mean, so I think there's still quite a bit of uncertainty. But I do think, there's processes in the sea ice system that I think would add noise to the system that we don't include in our climate models. Things in the Antarctic like wave ice interactions, which can also affect the Arctic margins. We don't include those. That actually, I think, would lead to less predictable conditions. Also, things like the surface heterogeneity of snow on sea ice. That's something I'm particularly interested in right now. But I think that there might be processes in our models that are giving us too much predictability. But again, I think it's still kind of an open question and something that really should be researched further. So yeah, it's a great question though.
Thank you, Francois, for attending as well. So let's keep going. The next question is from, please forgive my pronunciation, Sushitra Sundaram. She's asking, how does the intensity of the Ulusian low affect the Arctic sea ice during summer?
Yeah, so to the extent that the Aleutian low and its intensity will influence sea ice motion in the Arctic, I mean the winds over the Arctic Ocean, I think that there is some impact of the Aleutian low on the Arctic sea ice during summer, particularly in the kind of Chukchi Sea region. So that's another thing that at least the CESM does have some, so the Community Earth System model does have some deficiencies in its simulation of the Aleutian low. And so that could impact things like our summer sea ice in the Arctic and also the variability of that summer sea ice associated with things like the intensity of the Aleutian low.
Thank you. I'm trying to go fast. The next one is from a PhD student. One of those are working here at CMCC, Yulia Selivanova. Her question is about the impact of extreme cyclones on sea ice predictability.
Yeah, so I expect that at least on these seasonal timescales, extreme cyclones would contribute to a loss of predictability on these timescales. In that, those extreme cyclones aren't predictable on very long timescales, and they both dynamically and thermodynamically affect the sea ice, causing changes in ice motion and things like ridging, but also causing changes in the heat available to sea ice, for example. So I think that this is another area where climate models and the resolution that they're typically run at could mean that those extreme cyclones aren't very well simulated. And so it could be another one of these processes that might mean that our models are a bit too predictable, because I think extreme cyclones will affect the predictability characteristics of the sea ice. I also think that it's something that is likely to change over time, because things like extreme cyclone winds and the impact on ice motion and ridging is going to depend on the thickness of the underlying ice, how easily moved it can be, how easily ridged it can be. So it's another one of these aspects of, you could have the same number of extreme cyclones, but they might have a larger impact on sea ice in a thinner, warmer Arctic. So it's one of these things that, again, I think requires further study, but it's a really important question.
Okay, thank you again. The next one is a question from an old friend, Tony Rosati. Hi, Tony. Nice you are here with us. The question by Tony is, if we return to reduce CO2 conditions, will the sea ice extent return to conditions before the 2000?
Yeah, so there have been several studies that have done this, sort of ramped up CO2 and then ramped down CO2 and looked at the impact on the Arctic sea ice. And so the short answer is yes, that the sea ice can recover. There's not sort of a tipping point in the sea ice cover. So the sea ice cover will sort of follow the CO2. There's a time lag associated with that, but the time lag isn't huge. You know, it's more on the order of decades than centuries. So if we could indeed reduce CO2 concentrations in the atmosphere, the indications are that the Arctic sea ice would recover. So that's
so we still have some hopes.
Yeah.
But the next question, I think, well, sorry, what happened here? Yes, I lost it, but I think it will be fast, unfortunately, to be answered, is by Andrea Castelletti. So he's asking, is it almost sure that we will have ice-free Arctic within 2100?
Yeah.
So
I think the closer is, so I mean, most climate models simulations suggest that the Arctic will go ice-free in September, you know, somewhere around mid-21st century. And again, they can differ by, you know, 20, 30 years or so. But if we continue on the path we're on with greenhouse gases, I think that's almost certain to occur for the month of September. Again, we could recover that sea ice, however, if we reduced greenhouse gases. So I think it's very likely we will reach ice-free summers, ice-free Septembers in the Arctic. But also what our climate models project is that, you know, September goes first, but then you start eating into other months, and you can actually get a very long ice-free season, multiple months, you know, if you continue to warm the climate. And so it's not just a question of reaching an ice-free September, it's, you know, how long that ice-free season length is. And so I think, you know, the best hope for avoiding this and all of the repercussions it has is to reduce our greenhouse gas emissions. I mean, that's the simplest way to save the Arctic sea ice. So, yeah.
thank you, Marika. Again, another question from Gary Wolf. Is asking, what does the higher predictability for the 2010 initial condition, as you showed that in this specific period, that there is an increase of predictability. So what does this higher predictability in this period imply for public policy, if anything?
Yeah. Well, I think it's important, and this isn't something that I'm doing currently, so there probably are people that would have more expertise in answering this question. But I do think it's important for stakeholders and public policy around things like marine access in the Arctic to understand that, you know, the predictability characteristics of today on, you know, thinking about seasonal to perhaps annual timescales might be different than it is, you know, 5 years from now or 5 years previous. I think the fact that our climate model simulates this highest predictability in 2010, I wouldn't put tons of stake in that particular 2010 number because there is, you know, there's biases in our climate model. But I think this aspect of changing predictability characteristics in the Arctic is something that we need to consider when we're actually doing and providing seasonal forecasts. And if we're basing the skill of our seasonal forecasts on kind of hindcasts that have been done over the last, you know, 30 years or so, when we've had good satellite observations to initialize those, it's good to consider that actually those predictability characteristics could be changing over time. And that might have implications for, you know, how reliable they can be for stakeholders. So, yeah.
Thank you. Marika, is it okay with you if we take 5 more minutes? Because, we said in 1 hour we would have been done, but there are so many questions. And this one in particular, I think, is the one that I would have liked to ask myself by Kalpesh Patil or something similar. So regarding, deep learning, artificial intelligence, techniques. What predictors is asking are significant if we consider predicting sea ice extent using the recent deep learning framework?
Yeah, so it depends on the time scale, which predictors are important. And it also depends on the season for the sea ice. So, I mean, a lot of work has shown that summer sea ice, that a good predictor of summer sea ice is the thickness of the sea ice the previous winter. For winter predictions of sea ice, there's a lot of indication that ocean heat content anomalies, say in the North Atlantic and North Pacific, as the sea ice is moving into those regions over the winter, that ocean heat content can be a good predictor for where the ice edge location might occur. So it's so there are these predictors, these sort of long-lived aspects of the system that could be used in a deep learning framework, to look into using that for predictions. And I think there's quite a bit of work being done in that area. If you're trying to predict a few days out, the motion of the sea ice is really important, and that motion is very dependent on the winds. It depends on the time scale, it depends on the season, but we do see important predictors that could be used in this sort of framework.
There is a recent work that came out in Nature Communications last August about the use of deep learning in general for prediction at seasonal timescale. I don't know what we should do. We have so many other questions. Okay, let me read this one because it's from somebody I don't know. The other ones I know, probably we will have the chance to ask at a later, in the following days from colleagues here. By the one by Sylvain Marchi, not sure if I pronounce it correctly, sorry, I'm very sorry. As you mentioned that a good sea ice state is important to predict the sea ice and the seasonal to decadal timescales. Would it be relevant to include perturbations in the sea ice initial state rather than only in the atmosphere to study the inherent predictability of the sea ice at seasonal timescale? So that's related more to modeling setup, modeling framework.
Yeah, I mean, I think in these idealized experiments that we've been running to try and understand the inherent predictability characteristics, basically we want kind of a near perfect initial state, and so that's why we do that in that way, and that's because we're trying to just understand what is the inherent predictability. I think when you start getting to what can we actually forecast, however, how skillful can we forecast the sea ice? So not these kind of more idealized, studies, then yes, I mean, including errors in your initial sea ice state in those forecasts, I think will be important for producing an ensemble that has the kind of uncertainty that is really there in the system. And I think, it sounds like you're going to have Mitch Bushik talking to soon, and Mitch is, leading a lot of work in this area of actually forecasting sea ice and how we initialize those and things like that. So definitely say come back for Mitch's talk because he'll give a better answer than I just did.
Okay, I promise this is the very last one, okay? Because they're starting to tell me that we are going too long, and for you too, especially. But this is the one I would like to close with this question from another friend of ours, Yushi Morioka from Japan, from Jamstack. What do you think of the impact of ocean initialization on the Arctic sea ice predictability from seasonal to multi-decadal timescales? For example, the impact of ocean heat transport from the North Atlantic.
Yeah, I think it's critical actually to produce skillful forecasts, and it's critical. It's more critical in certain regions. So for example, the Barents Sea region, where ocean heat transport from the North Atlantic is a really important aspect of the sea ice variations in that region. And also the winter ice edge more generally, and the Greenland, Iceland, Norwegian Sea, the Labrador Sea, and the Bering Sea. Ocean heat content anomalies, again, are one of the primary predictors for sea ice in those regions in the winter. So I think having a good ocean initialization is critical for predicting sea ice, especially in particular regions, and especially in kind of non-summer months. In the summer, ice thickness, I think, is the critical thing, but it's not the only thing. But yeah, I mean, I think ocean initialization is really important.
Okay.
And just so we're about to be cut off from questions, I put my email address back on here. I'm more than happy to continue the discussion by email. So, you know, if you have questions, definitely feel free to email me.
Yeah, indeed, we have other questions, but from colleagues here in Bologna. So Stefano, Elena, please forgive me. We will contact you for sure in the very early future. So thanks again, Marika, for your time, for your patience in answering all these questions. Thanks again for your work.
Thank you. Yeah, thanks a lot.
And thank you to everybody for being still connected. It means that what you're discussing is very important and relevant for a large community of scientists. Thank you, Marika. Have a good day. Bye. Bye to everybody.